We're now going to move on to chapter 21, which starts looking at buffer solutions. So what exactly is a buffer solution? Well, they're a chemical that act to stop the change in the pH. And so what you could do, you could add these to all sorts of other mixtures, and what it would do, it would actively prohibit the pH from changing. It's a chemical that is used up by this process. What it does is it does the opposite of the effect of adding the alcohol. It provides basically a base for the excess acid to neutralize with, keeping the pH approximately the same as it was before. Now, we use different bases for different pHs. Different bases will, in fact, keep the pH constant at different values of pH. So we have to be selective about which one we use. But to convince you of the importance of this chemistry, let me tell you about how these buffers are used every day. We'll go on to, in the next presentation, look at how buffers are used in the blood to regulate blood acidity to basically, well, the pH to be 7.4. It's also used in cosmetics like shampoos and in baking, but very importantly in food preservatives, those foods that are already acidic. The acidity is regulated. They're called acidity regulators, but trust me, those are buffers. So I'm going to use ethanoic acid as an example of a buffer, also known as acetic acid. So a buffer, in this case, is if I introduce both ethanoic acid and one of its salts, in this case sodium ethanoate, which is like ethanoic acid, except it's had its hydrogen replaced by a sodium ion. If I introduce them both to my mixture, then what I'm going to have is an acid and its conjugate base, both present. We can see here is the structural formula of both of those. So what effect would having an acid and its conjugate base have on a mixture to which I'd added? Well, it's a little bit about what they add to the solution. You see, if I think about the ethanoic acid by itself, and we call that component 1, it's going to partially dissociate in solution, forming a small reservoir of H plus ions. Now, if there is like an addition of any alkali, or if the substance tries to turn alkali, it's going to neutralize with this reservoir of H plus atoms. Now, the other side of it, the salt, the sodium ethanoate, is also soluble, and when it enters into solution, what we're going to find is because it's a salt, the ions, the CH3COO minus ion and the Na plus ion, they're going to separate, as salts do in water. So what that means is it is sitting there ready to accept any H plus. It is basically it is a conjugate base. It's ready to neutralize any excess acid that might appear in this solution. Now, this, as an example, using an acid and one of its salts as a conjugate base is, of course, really straightforward. But what we could use is any aqueous solution of alcohol, like sodium hydroxide, with any weak acid. It's just that this is a very nice example, so that's why we use the ethanoic acid. Now, the best way to think about this is that there are two reservoirs. There's a reservoir of hydrogen donors and a reservoir of hydrogen acceptors sitting within this mixture. Now, of course, it's an equilibrium, and if I added an acid or an alkali to this equilibrium, it would shift the position of the equilibrium. In fact, it would favor the conditions that would be required for the elimination of that change. So if I added acid, I would favor the conditions for the neutralization of acid, and more acid would be neutralized than the reverse process, and so it would essentially eradicate the change I had made. It is a fantastic example of Le Chatelier's principle. For example, in more detail, if adding an acid shifts the equilibrium to the left, then it actively removes the H pluses that have been added by the addition of that acid. And so, no matter what I do, I shift the position of the equilibrium to undo the change that I've just done. But generally, thinking about it not as an equilibrium, but basically as two separate reactions, and that they are happening with two reservoirs, we have a reservoir of H+. And so the addition of OH- would have it turn into water. And with the reservoir of CH3COO-, a reservoir of ions willing to accept a hydrogen, if H+ is added, then we get undissociated ethanoic acid back again, which undoes and lowers the concentration of H+ ions, undoing the effect that adding acid or alkali has had. Now we need to be able to choose a buffer that keeps the pH at the value that we want it to be. And so we have to choose quite wisely. What we find is that they work most effectively when there are equal concentrations of weak acid and conjugate base in the solution. Now what we'd find is if we were working at a different pH value to the one that the buffer works most well at, then we'd find that there was a significantly higher reservoir of component 1 compared to component 2, and one would use up before the other, and then we'd lose the regulation on the acidity. Now, at this point, where they're approximately equal, we have the maximum capacity to resist changes in pH. So we've got the reservoirs are both full in equal measure, and so we have a huge capacity to resist that change. Now, an operating pH of a buffer is over about 2 pH units, which is about a factor of 100 on the concentration of the ions present. It's centered at the pH of the powers of the dissociation constant value. More about that on the next slide. So here are some nice examples. Now I'm only giving here the weak acids. Of course, you would have to mix also a conjugate base in for these buffers to work. So don't believe that just adding an acid is going to do anything other than increase the pH. You have to add an acid and a conjugate base at the same time. Now, ethanoic acid is the one that we previously looked at. It has this partial dissociation of the hydrogen on the far right, and we can measure that dissociation and we can summarize it with the power of the dissociation constant pKa, and it's equal to 4.76. And this is the peak of the pH range that it will keep stable. So it actually is effective between a pH range that is smaller than this and larger than this by about 1 pH either way, so down to 3.76 and up to 5.76. Other acids like glycolic acid and methanoic acid, otherwise known as formic acid, different pHs, they would regulate the pH if it was an acidic substance that was needed. So you'd probably want your lemon juice to stay acidic, so you'd probably add a buffer when you package that food item to keep it at the right pH. And of course, lactic acid that builds up in your muscles when you are undergoing anaerobic respiration. That is also quite acidic, and so that will keep the pH range between about 2 and 4. Now you may have noticed from that last slide that the power of the dissociation constant pKa was equal to the center point of the pH range over which a buffer was effective. So why should that be? Well, let's go on a deep dive. If we imagined just an acid HA was partially dissociated into H+ and A-, and this was the acid in our buffer solution, we could write a dissociation constant Ka, and like all of those, it's the products divided by the reactants, and so it's the product of the H+ ion and the A- ion divided by the original concentration of the HA. We could rearrange that to get it in terms of the H+ ion's concentration. H+ concentration is equal to the dissociation constant times the ratio of the concentration of the original acid to the concentration of the A-. Now, imagining all of your buffer is used up, then what we'd find is the amount of A- that was present was equal to the actual concentration of the original buffer solution that you added. So therefore, the concentration of HA would be equal to the concentration of A-, which makes that relationship there, that one in the middle, quite tidy because it would be equal to A minus divided by A minus. So it would essentially mean that that ratio on the right-hand side was a 1-to-1 ratio, which 1 divided by 1 means that the whole right-hand side just becomes equal to 1. And so what we find is that the concentration of the H plus ion becomes equal to the dissociation constant Ka. And so therefore the power of hydrogen, the pH, would be equal to the pKa. Well, that's all great and good, but now we have to actually apply this to some calculations. So take a look at this worked example. Wants to know the pH. There's a buffer added, and it gives the concentration of the acid as 0.1 mole per decimeter cubed, and of the conjugate base 0.3 moles per decimeter cubed, and it also gives the acid dissociation constant Ka as equaling 1.74 times 10 to the minus 5 moles per decimeters cubed. So the strategy to employ here is we need to straightforward work out what the concentration of H plus ions are. And we can do that from the pieces of information that we have, Ka, Ha, and A minus. So let's have a look at that step by step. So going to the formula that we had before for the H plus ion was equal to the acid dissociation constant Ka multiplied by the original concentration of the acid divided by the A minus concentration. Here, well, we have some of those numbers. What we have is we have the amount of COOH concentration is 0.1, and we have the CH3COO minus concentration as 0.3. So what we just simply do is we substitute these values into this formula, and it comes out the concentration of H plus ions is 5.8 times 10 to the minus 6. The second step, because it asked for the pH and not the concentration, is we have to add it to the pH equation. So what we would do, the pH is equal to the negative log to the base 10 of 5.8 times 10 to the minus 6, comes out that the acidity, or the pH, is 5.24. So a more complicated question here. I'll give you a second just to read it. It says that 150 centimeters cubed, as a volume, of 1 moles per decimeter cubed, that's a concentration, of HCOOH, that's an acid, is mixed with 100 centimeters cubed, that's a volume, of 0.750 moles per decimeter cubed, that's a concentration, of HCOONA, that's a conjugate base. Calculate the pH of the buffer solution formed, and they give you the dissociation constant. Tricky. It's tricky because it's not really clear what has happened. First, what we're doing here is we're mixing the buffer solution we're mixing together an acid and its conjugate base. We're preparing the buffer solution. And we know that because they gave volumes and concentrations of both components. So what we have to do to proceed with this sort of concentration is we have to work out what the concentrations are of the mixed solution rather than these two solutions independently. So the very first thing we need to do, given that there's different volumes and different concentrations of the acid and the conjugate base, is we need to first calculate the number of moles present in each of these volumes. Then we're going to mix that together, and from the numbers of moles present in this new total volume, work out what the concentration is of the acid and the conjugate base in this mixed buffer, and then proceed with the same steps as in the question before. So let us first work out the number of moles. Now, if our concentration is in moles per decimeters cubed, and we multiply it by the volume in decimeters cubed, we would get the number of moles because the decimeters cubed would cancel out. But we have not been given the volume in decimeters cubed, we've been given it in centimeters cubed. So what we need to do is we need to first convert that volume from centimeters cubed to decimeters cubed. So the 150 centimeters cubed has to be divided by 1,000. That's why the 1,000 is in there. Now, we take 1 mole per decimeter cubed and multiply it by the actual volume that we've got. We work out there's 0.15 moles of the acid going into our mixture, into our buffer. Now, we can do exactly the same with the base, and we get to 0.075 moles of that. We're going to mix these two together to form a solution that has a total volume of 250 milliliters or centimeters cubed. Now, if you remember that the formula for concentration is N over V, here, N divided by V isn't exactly what it shows here. Why have I got 1,000 divided by 250 looking at the bottom sections here? 1,000. Well, what we've done here is I have taken my N, 0.15, and I am dividing it by my volume. But my volume itself is in centimeters cubed, and it needs to be in decimeters. So I'm taking 0.15, dividing it by 250 over 1,000. Now, taking 0.15 and divided by 250 over 1,000 is the same as multiplying 0.15 by 1,000 and dividing it by 250. So if you wonder what's happened there, I've just ups the daisy the fraction to put it's a number divided by a fraction, then basically it flips it upside down. So my answer was, in the actual 250 milliliters, I had 0.6 moles per decimeter cubed. And with the conjugate base, I had 0.3 moles per decimeter cubed. So knowing the concentration of the acid and the concentration of the conjugate base allows me to put these into the formula that we used before, multiply by the dissociation constant, and get the concentration of H plus ions in this solution equal to 3.56 times 10 to the minus 4. Of course, this concentration of H plus ions can be put into the pH equation. The pH is equal to the negative log of 3.56 times 10 to the minus 4. It gives a pH for this solution of 3.45. Well, I hope you're ready for this, because here comes what I think is the hardest question relating to buffers. What we've got here is not a pre-made buffer, and we haven't even got a conjugate base. But what we're going to do is we're going to use some NaOH to neutralize some of the acid present to form the conjugate base in the first place. And what it wants is to calculate the pH. So let's read through the question first. These are really tricky, so you're going to have to practice these. It's 100 centimeters cubed of volume of 0.75 moles per decimeter cubed concentration of sodium hydroxide. Whenever you see a volume and a concentration together, your instinct should be to calculate the number of moles present. Even if it's not what you need to do, it quite often is, so I would just automatically start working out some numbers of moles. Now this NaOH is added to 150 centimeters cubed, that's a volume, of 1.5 moles per decimeter cubed of HCOOH. We can work out a number of moles there. Calculate the pH of the buffer solution formed, where they give you the dissociation constant. So just be aware, the NaOH is not the conjugate base for HCOOH, but it will produce it. So what we need to do in the step-by-step of this, and notice the question never prompted you for this, and that's why I think these are so hard. You must write the balanced formula for the production of the conjugate base. You're going to need to work out how much conjugate base you're capable of producing from that sodium hydroxide. Once you're there, it then follows steps like on the previous slide, calculating the number of moles in the buffer solution of the conjugate base, calculating the number of moles of the acid in the buffer, calculating the number of moles remaining. So let's have a look step by step with a work through. Once we've identified what we're doing, this first step becomes quite straightforward. So the balanced formula for the production of the conjugate base is that some of the HCOOH being added to the sodium hydroxide is producing that salt of the ethanoic acid, the HCOONA, the sodium ethanoate, and some water. And so that's great. We can see that it's a 1 mole to 1 mole ratio for that happening. So fantastic. We know that for every mole of sodium hydroxide we've got, it's going to produce 1 mole of our conjugate base, sodium ethanoate. So therefore, well, we haven't got 1 mole. Let's work out how many moles we've actually got. So if we remember that to work out the number of moles when we've got a volume and a concentration is, well, the number of moles is going to be equal to, it is CV, N equals CV, so it's the concentration times the volume. So what was the volume? It was 100, but that was in centimeters cubed, so we have to divide it by 1,000 to get that into decimeters cubed, times the concentration, 0.75, gives us 0.075 moles. Well done, we've worked out how many moles. This is going to be equal to how many moles of sodium ethanoate we've got. We also want to know how many moles of the acid we have, so we just compute the numbers that we're given for the acid, and we work out 0.225 moles. On to the next step. But here comes the terrible detail. Remember at the start, we were producing the conjugate base from the acid, and we produced some moles of sodium ethanoate from it. We've also depleted the actual ethanoic acid. It has reduced by the amount we have converted into sodium ethanoate. So what we now need to do before we can do anything is just work out how much is left of the ethanoic acid. Now, we know how much we had to start with. It was 0.255, but we have lost 0.075 because of that reaction. Some of it has turned into sodium ethanoate. It means that the actual amount of acid that we have in our buffer is the original amount, but take away how much was used for the production of the conjugate base. It means that we've only got in the end 0.15 moles of the acid remaining. And so what we do with this now is, well, we've now got the amount of acid remaining and we've got the amount of conjugate base in moles, and so this is going to be computable just like in the previous examples. What we can now do is work out the concentration of the H plus by multiplying the dissociation constant with the fraction of the concentration of the HCOOH to the concentration of the HCOO minus.